Hi, hello class. So as you can probably tell, my setting has kind of changed. I'm now in college, so we have the college teaching setup going on. I have a whiteboard in my hands, and things will be a bit different. Won't have my normal kind of supplies, but let's begin. Today's video, kind of going hand in hand with my own new change. We're introducing kind of a big topic here in calculus. We're going to be talking about what an antiderivative is, or otherwise known as an integral, what antidifferentiation means, and we're going to do some unbounded integrals today. Take some antiderivatives, and I'm going to show you a couple techniques. So, first of all, textbook definition. I'm going to go ahead and say that let f prime of x equal this function, capital F of x, right? And so now, the deal with this is, with antiderivatives, if we think of f prime of x as this kind of big F of x here, if I were to take the integral of big F of x with respect to x, right, and I'll explain more about this dx kind of later, this is actually going to be equal to function f of x. And then remember, we always have to include our constant of integration plus c right now. So I'm throwing it a lot at you. We'll review this, but this is essentially saying that the integral, the antiderivative of f, big F, with respect to variable x, is going to be equal to function little f, right? As such, now if I were to take the derivative of f of x, little f of x, I'm going to in fact get big F of x here. Now, the biggest example is, and now before I even teach you anything, let's just say the integral of 2x dx. I know that this is going to be, personally, I know this is going to be x squared plus c, our constant of integration, right? Now, if I were to take the derivative of x squared plus c, I would in fact get 2x, right? And so integrals and derivatives, or derivatives and antiderivatives, are inverse operators, right? And again, an operator is simply some sort of operation you do that turns a function into another function, right? So let's talk about this dx a bit more, this differential. We've talked about differentials before in this class. In our last video, we talked about why we have this dx, right? I'll draw the typical math teacher graph. It looks something like this. When we're integrating, right, and I went over this in the last video, we're going to be adding up a bunch, in fact, infinitely many of these super tiny areas, right? And the width of each one of these rectangles that I just drew is going to be dx. The width is going to be dx, and the height is going to be f of x, right? And so that's another important kind of, that's the reason why all of this works. We have a width of dx, and that width is actually infinitely small, which is difficult to think about, but it's how integration works, right? And the height is large f of x, right? And now, so I told you that we were going to do some integration techniques, because integration, we have to know how to do integration, not just what it is, and I'll keep up on that promise. So again, that was more of a textbook definition, what we just did. Really, an integral is just going to get you the opposite of a derivative. You take a derivative, you're going to get a slope, right? Derivatives represent slopes. Now, integrals are going to represent accumulations of change. I believe I briefly touched on this in my last video. So yeah, they're opposites. And it turns out that areas and slopes in math give you the opposite things, which is really, really convenient for us, especially if you talk about physics or something. Now, okay, integration techniques. We're going to first talk about the power rule. I'm going to have two examples, and I'm going to teach sort of through this example. Two very simple functions. 2x, that is a line. That's a linear line. X squared, that's a parabola centered at 0, 0. Now, you might already know this, or you might have caught on from my previous work with this integral, but the power rule for derivatives works very similar to the power rule or inverse power rule, whichever you'd like to think of it as, for integration. Now, for integration, it is simply, the way I'd like to think of it as is add 1 to the power and divide to the power. Now, in application, that would look like this. we're going to take 2x, we're going to add 1 to the power of x, the variable we are taking the integral with respect to. So this would become 2x squared. Okay, and then we're going to divide by the new power that we just created, which in this case, since we just raised the power by 1 and our result is 2, we're going to divide by 2. And don't forget that plus c. Remember, that plus c is important because when we take an antiderivative, we're going to get a new function, but that function's y-intercept could be anywhere. Remember, the derivative of a constant is 0, so when we have an antiderivative of 0, we have to get some sort of constant, but we don't know what that constant is. In real problems, you'll be given an initial condition, right? And we can go over that in a second, right after I do this example too. Now, integral of x squared with respect to x is going to be, okay, we're going to add 1 to the power, it's going to be x cubed, and then divide by the new power, which is 3, right? And then don't forget plus c, that constant of integration, right? Now let's talk about the constant of integration a bit more, and with initial condition. A lot of times you'll be able to solve for plus c. Now, what if I told you, okay, f of x is going to be equal to, let's just give it over here, x squared plus c. Let's say f of x is equal to an integral. You solve that integral, you get x squared plus c. But you're wondering what c is. Now, let's say f of x represents some sort of velocity of an object. And now let's say that object starts from rest. Now, if that object starts from rest, its initial velocity is going to be 0, which means that f of 0 is in fact 0. And now we have kind of a constraint here. We have a bound that we can think about, and this can help us solve for c. Now, if we know f of 0 is equal to 0, we can plug in 0 for x and set that kind of function equal to 0 like this. 0 will be equal to 0 squared plus c. And now I've chosen this problem such that c is equal to 0, right? And now that we know that c is equal to 0, we can go back up to our original f of x of function and just plug in c for 0, or 0 for c, and then just get x squared, right? And so initial conditions, usually given in the context of a problem, are going to help us solve for that unknown constant of integration when we are dealing with unbounded integrals, right? Sorry, I'm going to be spending a lot of time erasing with this new tiny whiteboard that I'm carrying in my hands. All right, so to go in more depth on like a textbook definition of the power rule or integral power rule, if you would like it, we're going to say that the integral of any x to the n with respect to x is going to be equal to x to the n plus 1 divided by n plus 1. Right, where n is simply a number. It's simply an integer, right? Cool. Now, just like with derivatives, this can get a whole lot more complicated. We can have a power of 3/2. We can have a power of 1. We can have a power of 0, which is weird because that'd just be a constant, right? So that's something I'd like to touch up on next. If we just integrate a constant, say 7 dx, we are going to get 7x plus c. Right? And so when you have a constant, you simply can just add that variable when you integrate, right? That integral, you can think of 7 as 7x to the 0th power, right? And then when you integrate, you get 7x to the first power divided by 1, which is just equal to 7x, right? And now I'd like to go over a very important rule that you can utilize with integration. Let us say we have an integral of I'm going to go with 7x, right, dx. Very similar to our last example. Now, with constants, we have recognized that constants, much like with limits in our limit laws, aren't going to, well, they will affect our integration, but think about this, you know, if we were to take the integral of 7 with respect to x, we will get the same thing as if we just took the integral of nothing with respect to x. So this integral is actually going to be equal to 7 times the integral of x with respect to x, right? And that's an important identity. What this is saying is that you can essentially take constants and you can just bump them out in front of the integral, because multiplying the integrand is what is inside the integral, right? Multiplying the integrand by the constant is the same thing as multiplying the result of an integral by that same constant, right? And I can prove it to you here. This would equal 7/2 x squared plus c, and this one would be equal to 7 times x squared over 2 plus c, which I mean, as you can see, is the same thing, right? It gets a little weird, but yeah, that's an important identity. You can bump constants out, but, well, and that can help you a lot in solving tricky integrals, especially if you have like weird numbers that might get in the way there. However, it is important to note that you cannot simply bump out a variable out of the integrand. The variable must stay inside the integrand, given that you are taking like an integral with respect to that variable, but that's besides the scope of this class. If you have an integral with respect to x, you're really only going to be integrating x functions in there. You're never going to see stuff with like x, y. Okay, now, here's another important integration law. I know I'm going through a lot here, but let's take a polynomial function. Say x squared plus 2x minus 7 dx, right? Now, we have this polynomial of 3 terms, and I claim that this integral is in fact equal to the integral of x squared dx plus the integral of 2x dx minus 7 times the integral of dx. Oh, I just wrote times x dx there. Really just say the integral of dx. Now this illustrates 2 important things. One is more subtle than the other. The first is we can split up integrals into a sum of integrals with addition. Now you see, because we have addition here and subtraction, we can simply split up an integral into a sum or difference of integrals. And now this can help a lot. Sometimes it isn't as helpful, but a lot of times it is, especially if you have like kind of 2 functions in there that you're worrying about and you want to split them up and integrate them separately. So that's kind of my introduction to that, right? And now the less subtle thing here is I have this weird term that's minus 7 times the integral of dx. Now the integral of dx is something that you'll run into, right? But what happens if you integrate nothing? It's weird. This is the same thing as the integral of 1 times dx, which would be simply equal to x plus c, right? So if you can simply just integrate dx, which sounds a bit weird, but think about it as you're taking the area of a function that always has a height 1 and has a like those infinitesimal widths of dx, right? And so when you integrate, you simply get x, right? Sorry, I'm erasing a bunch again. I'd like to get to, I think, at least one more thing, and it goes back to this example that I have on the board. So I said you can split up an integral into a sum of integrals, but again, I also said that sometimes that's not always the best way to do it. You can straight up do this entire integral. You can think about it as integrating each term separately, or you can think about it as integrating all at once. Now, I'll show you here. You can apply the integral power rule to each term of this separately, but all in one integral, and just do it all in one step. And I like to do that a lot. That'll get us x cubed over 3 plus, and then x squared minus 7x plus c. And now this works because of that separation of integrals rule that I taught about just a couple minutes ago. Because of that, we can think of an integral as simply a sum of smaller integrals, right? And now with that, I believe that's all of the kind of like basic rules of unbounded integration that I have to follow. There are a lot more, there are many more integration techniques, and in our next video we'll kind of talk about like bounded integration, which is when we will be plugging in kind of like bounded like endpoints to this function to, instead of getting another function which represents an antiderivative, we'll instead get an entire number, right? So anyways, thank you for joining me on this kind of this new transition setting, and I hope you enjoyed my new setup, and I hope you found this video useful. So goodbye, class. See you later.